Hello everyone, and welcome to today's session, Fundamentals of Heat Transfer in Gap Filler Materials. My name is David Zimmett. I'm the president of Orion Technologies, Fujipoly's representative in Canada since 2006. I'd like to introduce you to today's presenter, Christian Menegra, Fujipoly America Applications Engineer. Christian is a graduate in mechanical engineering from the New Jersey Institute of Technology and has been with Fujipoly for 8 years. So prior to beginning, we would like to ask you a couple of questions. And at the end of Christian's presentation, we will have a Q&A and would love to hear from you. The Q&A tab can be found on the top right corner of your screen. Christian will also show us a number of samples, and you will be able to preview and download a white paper related to today's session. The handout tab, once again, can be found on the top right corner of your screen. And when the webinar is over, we would truly appreciate your feedback about this session and future webinars. So we're going to start with a couple of questions we'd like to ask you. Here's your first question, folks. So are you presently using thermal management materials in your applications? So in general, it seems that most people who have answered have indeed used thermal materials. That's great. Here's your next question. What type of thermal interface material are you using in your applications? Here's your next question, a little bit more technical. Okay, so a majority of you are looking for high thermal conductivity, low thermal resistance, low compression force, and high dielectric strength in certain applications as well. Thanks very much, folks. Appreciate it. And here's your last question. Okay, a variety of different suppliers are being used in your applications. Thank you very much, folks. Appreciate it. So we will now proceed with Christian's presentation, and we'll follow that with the Q&A and some demos.
Hello everyone, thank you for joining us today. My name is Christian Menegra, and I've been a sales engineer with Fujipoly for 8 years. Fujipoly is happy to present today's webinar on the fundamentals of heat transfer in thermal interface gap filler materials. Fujipoly has been a manufacturer of thermal interface materials for over 30 years. We're perhaps best known for our expertise in silicone rubber, and specifically for our line of high-performing thermal gap fillers. Fujipoly is a secondary processor of silicone rubber, and we specialize in formulating the rubber with the goal of giving it properties not naturally inherent to silicones, such as thermal conductivity, electrical conductivity, and certain magnetic properties. Fujipoly America has its headquarters in Carteret, New Jersey, where we manufacture, package, and distribute our products for the entire Western Hemisphere. A couple of the topics that we're going to be discussing today for the purpose of the webinar, we're going to focus primarily on our thermal gap fillers. We also make other products such as gels, greases, and thin films. For the most part, the principles discussed will apply to those materials as well if you make changes to some of the assumptions. The topics are going to be Fourier's law of heat conduction, selection of an ideal thermal gap filler based on calculated temperature gradients. We're going to learn how to use a resistive network, and then we're going to take the resulting data and reference that to Fujipoly supplied information to help in material selection. We'll also be looking at some of the real-life impacts that one might come across, such as contact resistance, gap, impact of package and die sizes. We'll also look at some of the technical tools and resources available to design engineers. That'll just be a brief overview of some of the things out there. And lastly, we're also going to want to touch up on some of the newer products in our lineup and a couple of the interesting and exciting things that Fujipoly is developing that are going to soon be available. A few good terms to note. Thermal resistance definitely is probably the most important value to know for the purpose of our discussion. It's composed of contact resistance, which is a product of how well the material is made into each substrate, and bulk resistance, which is a combination of the thermal conductivity and the distance the heat's required to travel. So there are three components: the two contact resistance and the bulk resistance. Thermal gap is the engineered distance between the heat source and the heatsink. This is when a gap filler would be used. Compression is often a critical consideration along with the heat transfer. Commonly used units are going to include thermal conductivity, thermal resistance, power or heat dissipation, and heat flux. Fourier's law is going to be the topic of the next few slides now. Steady state heat conduction can be expressed using Fourier's law of conduction. Fourier's law of thermal conduction states that the time rate of heat transfer through a material is proportional to the negative gradient in the temperature and to the area through which the heat flows. It is expressed as a three-dimensional vector field. In this case, the material is assumed to be homogeneous and of constant K value. Here's Fourier's law shown in its differential form. It can be broken down into three vectors, one for each axis. Our material conducts equally in all directions, but in-plane conductivity is negligible since the heat will want to take the shortest path of resistance, and that's always going to be through the z-axis. So since we only need to concern ourselves with the scalar value of the heat flow, what we want to do is isolate the heat flow through the z-axis through a specific area. In most cases, this specific area will be the surface of a die lid, a multitude of components, or maybe some more complex geometries like a winding or some coils. We can rearrange the equation to find a given variable. Here we chose to solve for power and thermal conductivity. This is useful because the area is known by the size of the component, the distance is given by the gap being filled, the power is often but not always known by the efficiency of the component's performance, heat loss of the electronics as a product of its efficiency, and total power. Next, we're going to look at how to use a resistive network to come up with a thermal solution. The resistive network begins by giving thermal resistance values to the components of the total resistance. Another way to perform the analysis is to determine the required thermal resistance to meet your targets based on power and temperature target temperatures. Shown on the screen are the three basic components for thermal resistance in a simple system which consists of component, TIM, and heatsink. I mentioned earlier that the thermal resistance of the gap filler has three components. The other part of the system also have their own components such as heatsink, contact resistance, mass, and surface area. Whether there's any convection, etc. Since we want to keep things pretty simple for our study, we will assign arbitrary values for the junction and heatsink resistances. Those figures can be determined analytically, experimentally, or supplied by the component and heatsink manufacturers. The resistive network in series above joins each component by nodes. We make some assumptions, like each component being homogeneous. The nodes will be the points where we measure the temperature gradient. The sum of these resistances gives the total resistance of the system. Let's get into the analysis of a theoretical resistive network. We're going to use the equation rearranged earlier to solve for thermal resistance of the thermal interface material. We'll assign some values for maximum junction temperature at the die of 85 degrees C ambient, of 85 degrees C and an ambient of 40 C. The surface area is an inch squared, and the heat loss is 4 watts. That leaves us with the three resistance components. We're also going to assign arbitrary numbers for resistance of the package lid and resistance of the heatsink. Here we gave resistance of the die a value of 4 degrees C per watt, and the resistance of the heatsink was assigned a value of 5.2 degrees C per watt. If we rearrange our equation to solve for resistance of the TIM, you get the temperature gradient divided by power minus the two other nodes of our resistive network. The derived value is 2.05 degrees per inch squared per watt. Given this result, we now have the capacity to narrow down the material selection by referring to Fujipoly's technical data sheet at www.fujipoly.com. You can also refer to our Sarkhan guide, which is an excellent resource. This is an example of thermal resistance data we supply for each of our materials. The top table consists of some of our general purpose gap fillers. The resistance values for given thicknesses are listed as resistance versus pressure. We know from the resistive network analysis that our target is 2.05 or less. Circled in black are all the material options that would satisfy this requirement. Circled in red and typically made up of the thicker pads with higher resistance we show the ones that would not satisfy our requirement. The bottom table shows some of our high performance materials. All of these materials satisfy the requirement, but will carry a higher cost with the performance. So that's definitely something that you're going to want to keep in mind when selecting the material, because often people, engineers will want to go for the highest performing material out there, but the cost is definitely something to have in the back of your mind when you're looking at these materials and trying to decide which one ultimately is going to make it onto the design. So now that we've looked at the ideal gap filler, let's go over some of the problems one might encounter in real world applications. There are a number of unforeseen challenges such as heat flux on the lid, heat transfer down through the package, the direction of heat flow, and changes in resistance with compression, whether there's any convection being thrown into the equation is another thing to consider. And here's an analysis of the power density on the lid. In the real world, you might not be able to rely on the heat flux to look like it does on this graphic. Here it's of equal intensity, is spread out to the edge of the package. Power density expressed as watts per unit of area are most often calculated using the entire package surface. But in reality, the die inside the package is the heat source, and is typically much smaller. The thermal resistance of the junction from the junction of the die to the lid, and the heat then distributed on the lid can actually vary by quite a bit. So the bottom line is that a smaller surface is going to mean a higher resistance. Let's say we assume 10 watts of heat on a 1-inch square lid, but if 9 of those watts are primarily distributed towards the center and you only have 1 watt on the outer 1/4 inch perimeter, then the material really isn't doing much. This might create the need for a higher performing pad, or a designer might realize that they can undersize the pad and keep the same material and thus save some money on the cost, and still get away with using the same material. Keep in mind that the heat is dissipated in multiple ways. Heat can flow down through the solder into the substrate material to help dissipate the heat. In addition, thicker layers of copper can be used along with the thermal vias that will draw heat through and under the circuit board. We can also have convection if there's a fan in the enclosure. The tables provided by Fujipoly illustrate how thermal resistance changes with compression. We'll typically supply thermal resistance versus pressure at the 3 data points above to show how increased pressure and thinner bond lines will impact the final thermal resistance of each material at different thicknesses. So if you have a specific gap with tolerances involved, you're going to get a different thermal resistance depending on the tolerance and of the gap and of the pad. Supplemental data can also be made available upon request. Feel free to reach out to Fujipoly should you be looking for something not shown or published in our specifications. I also wanted to quickly touch on some of the tools and resources available to design engineers. Obviously one of the big ones is going to be CAD software and simulation, especially a simulation, heat transfer simulation, which allows to have a very detailed understanding of the heat flow, temperatures, temperature gradients. You can simulate stresses as a result of heat. You could easily try different materials by inputting the expected thermal resistance from the data provided by Fujipoly. It's a very powerful tool, the simulation tools. And then there's also more of a physical real world tool, which would be thermocouples and data loggers. If you have some kind of prototypes, or you have some device that you could test on, you could attach the thermocouples in multiple locations wherever you feel you need them, and you could actually log that data and see how it performs over time once it reaches a steady state condition. You could kind of visualize where the spikes are and where you might need to put some additional design work into. There are also some really nifty thermal and infrared cameras that'll give you a visual depiction of the temperatures and of the way that the heat is being distributed on the package and on the board. So that's something that's pretty neat as well. It'll also be able to tell you specifically what the temperature is at certain points. Then of course there's plenty of resources online, white papers, studies, And you could also reach out to Fujipoly and check out our website because we have lots of information on there as well. And quickly, just to summarize some of the things we discussed, we learned how to apply Fourier's law and how to create a resistive network to determine a target thermal resistance. You could use the same resistive network to determine a target delta T, which can then be used with the data on our data sheets to help in material selection. And then we also looked at the data sheets and some of the information available on our specifications, which again shows thermal resistance versus pressure, various thicknesses on the materials, and that's a very good guide to give you a general idea of what performance to expect. We also touched on some of the real world problems that might arise, such as heat flux varying on the lid and package, or other heat paths that may be taken, such as thermal vias, convective cooling that may be playing a role on what's going on in your enclosure. And of course, we just touched on some of the tools that are available out there, CAD and simulation software, thermocouples, data loggers, thermal imaging cameras, online educational resources. Again, please visit our website for more information. We have white papers, we have other videos just like this that detail more specific application information and material presentations. And quickly, just to touch up on some of the newer things with Fujipoly, we've got a couple new materials that have recently been introduced. We've got our PG45A and our PG80B, which are two new putties. And again, by putties, we mean they're thermal gap fillers that still come in sheet form, right? It's not a dispensable putty. It still comes in sheet form, but they are extra compressible. So we've got the new PG45A, which is a 4.5 watt per meter Kelvin. Still pretty affordable, but kind of borderline high performance. And then the PG80B, an 8 watt per meter Kelvin material, which is considered a high performing gap pad. It's a new revision on our popular PG80A. We've made some improvements. We've made it a little bit softer, and I think we've improved the price a little bit, so that's definitely a win-win situation. The GR130A is our new highest performing gap filler in our product line. It's a 13 watt per meter Kelvin material, so that's really exciting. And then coming soon, we have a GR14B, which is a new revision on the GR14A, but this is going to be a low oil bleeding formulation. It's a 1.4 watt per meter Kelvin. So some of the general purpose materials, lower cost, softer materials, they tend to have a higher oil content. So we're able to, keep that same soft, low cost material, but we've created a new compound that has a much lower content of silicone oil, so that's exciting. And then the GBR material is a 3.2 watt per meter Kelvin fiberglass reinforced thin film material, so this is considered a high performance for the thin films. It's going to have a great dielectric resistance as well. And just to remind everybody, engineering sample kits and custom samples are available. Feel free to reach out to your local sales representative, or you can go on to www.fujipoly.com and you could, right on our website, you could request samples, you could request pricing, you could use the Ask the Engineer tool, and we'll jump right on that and help you out. So thank you everybody for attending. I'd like to thank Orion Technologies, and now we're going to go into a quick Q&A session. Thank you.
We have a couple of questions, so why don't we start with the questions, Christian, and then we can maybe share some. You can show some samples to the folks who have attended. So the first question is, does surface roughness of a heatsink impact TR?
So with the gap pads and with the softer tacky materials, you shouldn't see any difference at all. That's why you don't have to necessarily go to a finely machined surface, which could get quite expensive. You could leave the surface with a certain degree of roughness without seeing much of an impact. If you're using like the thermal greases and the thin film materials, the impact might be a little bit greater because then you have the thinner materials that need to make their way into the rough surfaces. But overall, it's not usually a problem.
Okay. Here's your next question. How much does surface area impact compression force?
Yeah, it impacts it a lot. So the surface area, as the surface area increases, the corresponding deflection load is going to increase as well. That's why, sometimes it's easier to split up a larger pad into smaller pieces. It's not easier for assembly, but it could help you with the loads that you'll be experiencing. And
Okay. Thanks. How does reinforcement impact thermal resistance and compression force?
so the reinforcement, we have like an embedded mesh reinforcement, or we could actually laminate a reinforcement to either side of like a gap pad, for example. And we have the thin films also. They come as a reinforced thin film, or you could get it with the fiberglass reinforcement. So you are going to see a difference when when you introduce an extra impedance layer. The difference generally is not so large, but you might see something like in the range of 10 to 20%, depending on the material and on the thickness.
Okay. Thank you. Do you have outgas test data available for these new putties you talked about at the end of the webinar?
Yes, we put all of our materials through the ASTM E595 NASA standard for outgassing. It's one of the first things we do as soon as we decide that we're going to introduce a new material. We go ahead and perform the test on it. So that is available on demand.
Gotcha. Okay. Here's a multiple questions. Do the putties spread when you compress them? And do you need to undersize the pads, and how much should you undersize them?
Yeah, that's a good question. The putties definitely do spread. I mean, they essentially maintain their volume, right? So if you have, X and Y dimensions, and you know that you're going to compress it by a certain percentage, then you could estimate how the XY surface is going to expand with the compression. So given that, you might want to undersize the pad a little bit. That's going to help you lower the cost, and that's also going to help keep the compression loads a little bit lower. So it's definitely something you want to take into consideration.
Okay. We have another question here. Who is the supplier of CAD simulation software? And I know that in the circumstance of Fujipoly, your simulations are much more mechanical type simulations, right?
Yeah. I mean, if you're looking for a reference to some good CAD software out there, I mean, a lot of people use SolidWorks or PTC Creo. There's actually, I'm going to get back to Wendy with that one, because I know I've heard of one recently that's actually like an open source, like a free software which you can use to perform some thermal simulations. I just have to remind myself of what software that is, but there are a couple of open source free softwares out there that can be used.
Yeah. As a follow up to that, why don't you tell us a little bit about some of the simulations that you can do in house with the equipment you have?
Yeah, so I mean, the type of testing that we do is more of a physical mechanical type test. And, so we could actually compress a sample in between a heater and a cold plate, and it has thermistors embedded in it. You've got load cells to control the deflection of the material. And you could actually take measurements of thermal resistance and temperature drop through the thermal interface. And that's what we use to generate the data on our data sheets and in our catalog, right? We typically do 100, 300, and 500 kilopascals, so that we give you the thermal resistance over the different thicknesses of the material, and from low to moderately high pressure. And then we can also do some compression force testing, some tensile strength testing, elongation testing, a couple different things. We even have some environmental chambers out in San Jose, so we could do a little bit of accelerated aging, high temperature, different kinds of things like that. And with the compression test, so the compression test and the thermal tests are probably the most popular, especially the compression test nowadays, with the electronics being a little bit smaller, and the ease in which you can potentially damage solder mounted devices. So that's something that we could definitely help with.
What's typically the turnaround time if somebody comes and says, I don't know, uh, I'd like you to do a calculation of different pressure levels that are not found in your data sheet, something in
Yeah.
between those values.
Yeah, I mean, I like to say usually about a week. I mean, if there's urgency to it, we'll try to get it done sooner. If if we're in the office or if we're going to be out of the office, it might take a little bit longer, but it's generally about a week.
Okay. All right. Thanks for that. So, Wendy, we'll get back to you. Here's some more questions. How thick of a gap can the dispensable paste fill? And does the paste cure and harden?
So I mean that question is varied. The answer to that question is variable. Generally, we recommend staying at 1.5 or less, 1.5 millimeters or less on the thickness, just to be on the conservative side. We do have some materials that are stickier than others, and I've seen some customers go into to gap sizes up to 3 millimeters or possibly even more, and even on a vertically mounted application, right? So there are a lot of variables that go into that question. Uh, but if you want to take the 1.5 millimeters to be as kind of a loose rule, of course, we always recommend testing the material in your application just to be sure.
Right. We're
And the,
talking specifically about the paste, right?
yeah, so the paste, so we have two types of paste. We have the silicone, and then we've got a new line of non-silicone, and we're actually getting into the two-part RTV, room temperature vulcanizing materials, which will cure in place. And please stay tuned to Fujipoly for some information coming out on those. Hopefully next week, actually, we're hoping to put out a new release.
Okay. Here's your next question. What does sustain after 1 minute mean on your data sheet under compression force?
Sustain after 1 minute just means basically we go up to the 50% compression, and then rather than opening up again, we hold it there and continue measuring the load for 1 minute after we reach that 50% compression, just to kind of uh, give the customer an idea of how the material is going to relax, because the materials do relax quite a bit. The initial load tends to be quite high, and then it'll relax, and you'll have a much lower residual load over the long term.
Okay. Obviously, compression rate is one of the big challenges for engineers, right? Being able to control that pressure rate. Your compression rate data goes to 50%. Are you able to test for higher percentages? And how large of a pad size can you test?
Yeah, we could go higher than that. I mean, generally, uh, once we get down to a certain thickness, the reliability of the compression test gets called into question, right? Because we're compressing in between some metal plates, so it's not they're not exactly flat all the time, but we could do up to a couple of square inches, and definitely less than a half millimeter. Maybe once you start to approach like 300, 200 microns, that's when I start to get a little bit of nervous about how accurate the results are. But for the most part, we could cover a huge range of thicknesses and different sizes. Possibly up to like 2, 3 square inches or so.
Okay. All right. Any more questions, folks? Christian, why don't you show us some examples of some samples? I mean, I'm sure people would be interested in seeing, for example, I don't know. What do you want to show us?
Well, I'd just like to show you our sample kits, which, I think David, that we're pretty liberal with our sample kits. So anybody who would like to receive an engineering sample kit, please let one of us know, and we'll be more than happy to get you one of these. I mean, there's just, it contains a general array of samples. You've got some of the dispensable gel type materials, a variety of gap pads and thin film materials, some pretty decent sizes, but it's basically a snapshot of our entire product line, and it'll give you a good idea of the types of products that we provide. If you're not sure, looking for a little guidance on what to choose, it always helps to have a good variety of material on hand to feel out. Then we also have our other product line, which we didn't really talk about today, but I'll just show it to you real quick. We have some Zebra elastomeric connector sample kits as well, and these again they just contain a wide variety of different types of connectors, all different sizes, our different series. We have our carbon, our silver, and our gold. A little bit of a representative sample of each of in there. So it's
Okay.
pretty handy too. If you just kind of want to know what they are if you're interested in using a zebra connector, but you never have. It's always better to. It's always easier to have one on hand. Another thing I'd like to show, I think I kind of mentioned when I was answering one of the questions that some of our gap pads can be reinforced or we could laminate a reinforcement layer onto there. So that's something that's a little bit interesting. So here you've got like a 1 millimeter thick gap pad. And what we've actually done, we've laminated our GHR material onto this. So this is a glass fiber reinforced thin film material. I'll see if I can just separate it for you here. So there's a piece there. So, you could kind of see the thin film on one side and the gap filler pad on the other side. And this is really handy. I mean, for two reasons. One, it could help with the handling. Because some of these thinner, softer gap pads, uh, they have they tend to elongate a little bit, and the handling might be a little bit of a challenge in some cases, especially if you're using a larger piece. It helps to have some reinforcement. And then the other reason to have that possibly is for dielectric purposes. If you really need a good dielectric barrier in there, if that's something that's of high concern to you, then please inquire about our laminated products.
Okay.
And then the last thing I have here, I just wanted to quickly show an example of what a kiss cut sheet looks like. So kiss cutting is basically where you're cutting through the material, but you're not cutting through the bottom carrier. And the advantage of that is that it allows you to easily just remove the top cover film. And then, what you're left behind with is basically a laminated sheet with all of these cut parts on it. So then when it comes to assembly, you could just simply plug off, the individual pads. You don't necessarily have to handle a little piece or remove a liner from both sides. This is going to have the liner already removed. And it's a pretty convenient way of sourcing material and keeping it simple for people in the assembly lines.
Versus a kiss cut, right?
Yes, this is a kiss cut. We could also cut all the way through if it's preferred, but we do a lot of kiss cutting, and it's the way that most of our customers prefer to receive material. Works out really nice for us.
Okay.
And there's no tooling involved for the most part. If it's just a square or a rectangle, we could just cut it free of tooling cost. If there's any features, any cutouts or slots or holes, then that's where we would get involved with the tool.
Okay. In the interim, we have a couple of additional questions. Is the shelf life reduced in high performance materials?
No, the shelf life is not reduced. We have different shelf lives for different materials. So some of our dispensable materials come with an 18-month after date of manufacture. The sheet type materials, like the gap fillers and the putties are generally several years. They might vary from one material to another. So if you have any specific material that you're interested in, please go ahead and inquire with us, and we'll get you that information. But for the most part, there's several years, unless it's like some kind of dispensable material or maybe some kind of material with a pressure sensitive adhesive on it.
Okay. Next question. Does speed of compression impact compression load?
Yeah, absolutely. I think if you look at the charts, there was a question earlier about the relaxation or the sustaining the compression for 1 minute. So you
Right.
see the material relaxes substantially after it's compressed. So the initial compression rate is going to impact it. So a lot of what some customers will have to do, if they're having some compression issues, maybe they'll preload the assembly rather than torquing it all down in one shot. That's one way to go about it. And that will help you. So there's a couple of ways to help you keep the loads down, uh, running into challenges like that. And that's one of them, just slowing it down.
Okay. All right. I think that's it, folks. Christian, I'd like to thank you very much for your time and great presentation. For all the attendees, I remind you, we would really appreciate your feedback on the survey that will show up at once we end the webinar. We want to get your feedback as to what subjects interest you, so we can customize the next presentation based on your requirements. And thank you, Fujipoly. Thank you, Christian, again. Thank you, folks, for showing up at the webinar. And we'll see you soon. Thanks again. Take
Thank
care.
you. Thank you, David. Thank you, everyone.
Bye now.